super nervous about the state of things right now. So I hope everyone is doing well. No, I can't. I as much as I would love to watch Beastie Boys concert footage, I do have a moral duty to teach some things. So a couple announcements. So you saw in the chat, it was a busy grading weekend. So there'll be homeworks, grades posted Wednesday. The exams are all in. All of the medical and other deferments are done. So the exams will be back on Friday with complete scores. So the plan, so Friday we will be going through the exam question by question and working through everything. And I don't want to just post the solutions yet because I think that will lead to panic because everyone will be like, whoa, wait a second, this is much more involved than what I did. And I don't want that. I want everyone to think nice, happy thoughts about the exam. The complete scores for the homework scores will be, I'm trying to get most of them up this week. And the exams will be up by Friday. So a couple of the homework 4 might be posted over the weekend. Assigned reading this week there will be, but it is not. But there is not yet. I was trying to give you guys as much of a break after the exam as possible. So we're going to be with reading is going up this afternoon, and there will be a reading quiz that needs to be done for next Monday, right? There wasn't any pressing need for you guys to jump back in the reading and homework train, right? I think there'd be a mutiny, right? Beating you guys up doesn't serve any educational purpose, right? And so let you recover a bit from the exam. You'll also notice a general trend, right? We got through all the hard stuff, right? Now we're kind of on smooth sailing, and you'll see that with today's sort of lecture material, right? We're not really seeing anything super new, at least in this part right now. Okay, so a little while ago now, I think it was last Friday, was it? No, last Monday, a week prior to today, we talked a little bit about the types of diffusional phase transformations. And we started with polymorphic transformations, where we typically have a single material. It's not a mixture. And we just have different allotropes based on the temperature and pressure phase diagram, right? One of the most technologically important one is, of course, the phase changes that are exhibited by iron as we go through the temperature range at atmospheric pressure, right? At low temperature, we are BCC, and at higher temperatures, we go through an FCC back to BCC to liquid. If we go up in pressure even more, we get to epsilon iron, a hexagonal phase. We have many different allotropes of water depending on the pressure and temperature. Most of these are not particularly useful for engineering purposes because most of the time we're not dealing with pure substances, right? Most importantly are phase transformations like the precipitation reactions, right? Where we will hold for a while in a single phase region, quench down in temperature. So now we have a metastable single phase that will then, in this case, decompose. We have supersaturated metastable alpha. Beta, which is rich in B, will precipitate out, forming particles. And the composition of alpha will get leaner in B, richer in alpha as B-rich beta precipitates form, right? This requires long-range diffusion, and there's a global composition change. I mean, not a global composition change, but the composition of each phase changes, right? So this requires that we have B diffuse over long distances to form these beta precipitates, right? We also have eutectoid type reactions, right? Where we'll go from single phase gamma to two different phases, two brand new phases, in this case, alpha and beta, right? So this also requires long range diffusion, right? An example of this known in steel, right, is our austenite to ferrite plus cementite reactions, right? That we get in carbon steel, right? We also have a whole host of reactions that don't require long-range diffusion. So ordering, right? When we talked about solid solutions, we talked about how we can go from a random atomic distribution, right? That where there is no preferential sites to a ordered structure where there is, right? Again, this doesn't require a composition change and it doesn't require long-range diffusion. All we're doing is swapping sites, atoms locally on their lattice sites to bring about an ordered structure, right? And then we have massive transformations, which is where we transform from, in this case, beta to alpha at the same composition, right? So we have a change in crystal structure in this case, but not a composition change, right? So this also doesn't require long-range diffusion. So you can imagine that the kinetics of something like this is going to be much faster than a precipitation reaction, right? Whereas this precipitation reaction is going to be dependent on how fast we can move B through our system. A massive transformation is only going to be dependent on how fast we can do some local atomic jumps, right? And if we think about the time dependence of diffusion, right, that square root dt term that comes into our diffusion length is really the killer, right? On the other hand, it allows us to quench in our system. It allows us to stabilize a precipitate structure in a metastable state, which is one of the main ways we have for tailoring microstructures of materials, right?
When you say this does not require long-range diffusion, does that mean long-range diffusion makes this impossible, or it just isn't needed for here?
And here, for a massive transformation, it's not here, right? Because we're just changing we're keeping the composition is the same, right? We're going from beta of this composition to alpha of the same composition. So we don't need to move any solute over long distances. right? All we need to do is do some local atomic rearrangement. Right? So that's what I mean by long-range diffusion. Okay. So I'm going to talk a little bit about what seems like a detour and talk about interfaces between phases, interphase interfaces. And we'll see that this really isn't a detour in a minute, right? But if we have boundaries between different solid phases, right, we have two adjoining crystals that can have different crystal structures or different compositions, right? And so we're all familiar with the idea of grain boundaries. We have to think about now what happens if I have a boundary between an internal interface or an internal boundary between two different phases, right? And we can, whereas when we talked about grain boundaries a little bit, we talked about breaking them up through low angle and high angle grain boundaries. We have similar type of classifications for these interface boundaries, except we're going to call them coherent, semi-coherent, and incoherent. And these classes describe the atomic structure of the interfaces. And we're not going to get super detailed, but we want to be able to keep these terms and a physical picture of these in our mind. Okay, so if we have a phase alpha and a phase beta that have the same lattice separation, right? We have our planes that are approaching this interface. If they have the exact same separation, there can be a one-to-one correspondence. We can have perfect bonding across this interface, right? And we now have a strain-free, perfectly coherent interface, right? Coherent means that there's a one-to-one bonding, right? So the local neighborhood isn't altered across the interface. It's just we're, instead of bonding from an AA, we're now doing an AB type bond, right? Sometimes it's different crystal planes, right? So in this case, our A and B might have a different, alpha and beta might have a different crystal structure, right? But we can find planes in alpha that are well matched with planes in beta. And when we talk about particular crystallographic relationships, or when we talk about particular examples of phase transformations, we'll talk about orientation relationships that develop between two phases, alpha and beta, that give it, right? In particular, there's lots of famous interface relationships that show up in steel. The Kurgyamov-Sachs and the Nishiyama-Wasserman are two very important orientation relationships that allow a secondary phase to be rotated and aligned in such a way that it gives you a nearly coherent interface with alpha. But right now, let's just think in the abstract, right? And realize we can have different crystal structures that have the same spacing. Now, in reality, if I look at different planes, right, there's not likely to be very many of these. If I have different crystal structures, right, there might be one particular plane that gives me a nice coherent interface. But in general, most planes in alpha and B and beta are not going to have a correspondence. Right, so that's the first type of coherent interfaces, what we call strain-free coherent interfaces. More commonly, if we have a coherent interface, they're slightly distorted, right? This is highly schematic, but it helps you get the physical picture. If the lattice spacing between alpha and beta are not exact, but they're close enough, I can still maintain a one-to-one correspondence across it. But I now have a strain. I have a distortion. Near the interface, my A atoms are at a slightly different spacing than they would be in the bulk. And the same thing with my B atoms near the alpha beta interface, right? Here I have a tensile strain because these atoms are slightly farther apart than they would be back here. In B, I have a compressive strain because these atoms are slightly closer together than they would be back here, right? So I now have a distortion or deformation in my crystal, and this comes with an elastic energy cost, right? Right, I have to stretch all these bonds from their equilibrium positions, and that means I have to pay energy to do this, right? So a coherent interface, if the strains are, if the correspondence is close, can still be maintained, right? But obviously, what happens if this gets too large? What happens when I start the atoms, in order to maintain this coherency, end up being squished too much, right? Then we get what is called a semi-coherent interface, where edge dislocations pop into being, right, to give us, to relieve some of these strains, right? When the energy cost to create a dislocation becomes less than the strain, the energy cost to maintain the coherency strain, then we get a semi-coherent interface where edge dislocations pop into existence. This is really important in fabrication of semiconductor devices, right? So if you're depositing a material on a substrate, the first couple atomic layers are going to form a perfectly coherent relationship. But as you get thicker, the strain becomes too large, the strain energy becomes too large, and dislocations form, and it forms threading dislocations in your device, right? And this is a big area of research of Professor Grassman, right? Is understanding how to engineer and work with the formation of semi-coherent interfaces during the fabrication of semiconductor devices. All right, so a really important concept, right, that applies to much more than just this types of phase transformations that we're talking about this, right? And these dislocations that pop in are called misfit dislocations, right? And they serve to reduce the overall strain. So you can see now that I have the atoms at the interface are displaced much less relative to what they would be if there was a one-to-one lattice correspondence. Okay, and then the next bit, we take it a little farther. We have a fully incoherent interface, right, where we don't have a clear correspondence between atoms on one side and atoms on the other, right? This is, thanks Google. What did it find for me? It did find fully incoherent interface. How about that? But anyway, so we have we no longer have a lattice correspondence, right? And you can imagine now we have essentially all of these dangling bonds, right? None of the atoms at this interface are in their preferred state at all, right? We have a very high energy situation with an incoherent interface, right? But in reality, this is what we get most of the time, right? If you have interatomic distances that vary by more than 15, 20, 25%, there's no way that you can maintain any kind of regularity of the interface, and we end up with a fully incoherent interface, right? So if we look at the relative energies, coherent interfaces in the solid are going to have the lowest energy, so less than 200 millijoules per meter squared. Semi-coherent interfaces generally have a range of about 200 to 500 millijoules per meter squared. And then incoherent interfaces are the highest, right? But anyway, these are approximate, but they're generally true for a wide range of metals, intermetallics, ceramics, right? So just a good starting place to think about this if you don't know the actual values, right? And these interfacial energies are exceptionally difficult to measure. Okay, so why is this important? Well, let's look at a case where alpha and beta have very similar lattice spacings, and they have the same crystal structure, right? In this case, we have aluminum silver, right? And we have silver-rich clusters that form what are called zones, right? But what we see is that when everything works out, these can form low energy, fully coherent interfaces, and the precipitates will tend to take a perfectly spherical shape, right? And the spherical shape is because that is going to minimize the surface area to volume, right? And so we can take the lowest energy in our system. Our system can adopt the lowest energy by making spherical particles, okay? If our interfacial energy is anisotropic, we're going to get different shape precipitates. So imagine now we have this weird looking double hump plot. This is the interfacial energy as a function of direction, right? So if I look at the interfacial energy for this plane normal, it's much lower than if I went off at an angle, right? This distance here is much more, less distant here, and much less than in this direction. So when we have an anisotropy, we can minimize our overall energy by creating precipitates of different shapes. In this case, we're going to make a plate-like morphology rather than a sphere, because if we make a plate, we maximize the amount of this low energy interface that we have, right? So the interfacial energy is going to help determine the equilibrium shape, right? So it's a little counterintuitive sometimes when people think about this at first, because we end up with a lot more interfacial area when we have a non-spherical shape, right? But what we're trying to minimize is the overall area. So if by making a sphere, we make a large fraction of that interfacial area be a high energy configuration, if we squish it down into a plate, then we we can reduce the overall energy, right? And we see this is the different precipitate in the same aluminum silver, right? So the GP zones initially form, those are those perfectly spherical regions, and they're in this darker shading here, right? those are coherent and strain-free. Then this is another precipitate, this gamma prime phase, and these form along plate-like lamellar type precipitates because of the strong interfacial anisotropy between different crystal directions, right? So this is this understanding how the interfacial energy is going to affect the evolution of our microstructure is really important consideration with phase transformations. Okay. So let's think of a thought experiment. Okay. So in this case, we neglected any discussion of coherency strain. We just talked about the shape arising from the anisotropy and the interfacial energy. But now let's add in the notion of coherency strain, right? So first, let's consider the case where we still maintain a spherical shape because we have an isotropic surface energy, right? And so there was this guy named Eshelby who was trying to model this system, to model the understanding of what happens in a system when we go through these transformation strains. And he developed a thought experiment called the Eshelby inclusion analysis. And what he says is, let's take our perfect alpha crystal structure, and let's cut out a region that's our precipitate. Okay? And then we're going to transform it, right? So in this case, beta has a lower lattice spacing than alpha, right? So now when we do our phase transformation, the region we cut out has shrunk, right? And then we're going to force beta, we're going to stretch it back out so that it's exactly the same size as the hole we cut out, right? So now beta is under very, very high tensile stress state, right? We put it back in, we sew everything back together, and then we let go and let the system relax, right? And the compressive, the strain, or the beta's under a large tensile strain, it's going to pull back on alpha, and it's going to distort the lattice around it, right? So now, and it's going to do that up until the total strain energy in the lattice alpha is the same as the strain energy in beta. And from a classical analysis, we get a result that our stress state then becomes uniform in here. In the precipitate, that's not really important from for the discussion. But this is a really useful thought experiment to think about how the lattice is going to distort, right? So in this case, we maintain a coherent interface. We have our one-to-one correspondent. We can work through the same exact sort of thought process for a incoherent interface, right? Now we don't have, but we don't have the same correspondence, right? And so if we think about what is going to happen with the shape of the precipitate, it's going to be determined by a combination of the interfacial anisotropy and the anisotropy of the elastic stiffness, right? Some directions in a crystal are easier to pull on than others. They're not as stiff. Our Young's modulus has a directional dependence in a crystal, right? And so we need to consider that take that into an account as well. And one of the most well-known examples of this is aluminum copper, right? So aluminum copper, the equilibrium theta phase is a very large unit cell with a large with a fully incoherent interface, and it's very, very difficult to nucleate. So instead, we go through a series of intermediate phases, and the first that forms is the GP zones, which are just clusters of copper atoms, right? And copper and aluminum both form FCC, right? So the local structure in the GP zone is still FCC. But we have a anisotropy in terms of the interfacial energy and with respect to the elastic modulus. So we get a cluster here where we have, they form these plate-like or disc-like structures with a high degree of elastic misfit in one direction, perpendicular to the plane of the surface, and a much smaller interfacial energy, much smaller elastic distortion this way, right? And between the combination of elastic anisotropy and elastic anisotropy is overall what determines the shape, okay? This is not something you can generally predict a priori, right? You have to, this is not, predicting the shape of the precipitate is not easy to do, okay? So you're not gonna have to work it in that direction, right? Unless it's something really obvious where I say this plane has a very strong forms an incoherent interface, and this one forms a coherent. You can make some guesses, but quantitative prediction of the shape is a very difficult thing to do and requires some serious modeling. But just get a general sense of the picture is really what's important for this class. Okay, so here's what I was just talking about, right, is our theta phase here has a much larger unit cell, and it forms a fully incoherent interface. But this is our thermodynamically stable phase. This is the lowest energy phase, right? But we can't nucleate this big thing, and we'll talk about why in just a little bit. So instead, we go through a series of intermediate phases, right? First, we form the GP zones that form a fully coherent interface. Then we go to this theta double prime, which is semi-coherent, theta prime, which is also semi-coherent, but a little bit larger. And then the thermodynamically stable theta phase is a fully incoherent particle, right? So, right. So often we have metastable things that appear because we can get a gradual lowering of the energy of our system. If we waited until we had enough driving force to nucleate this theta, it would essentially never happen. So we can nucleate these GP zones homogeneously, right? From the GP zone, we can nucleate the theta double prime and theta prime heterogeneously from these GP zones. And then the theta can nucleate from the theta prime, right? And we'll talk about that in much more detail later. First, we need to talk about the theory of nucleating secondary phases in a solid homogeneously, and you'll see it's really very similar to nucleating solid from a liquid. Okay, but we have a free energy change due to this misfit, right? So we have a Gibbs free energy associated with the incoherency strain, right? That's going to be related to the elastic modulus, the shear modulus in this case, right? The misfit, the volume misfit, right? So we have a shear modulus times the misfit strain times the volume, and then this shape correction factor. Okay, so what's the energy of a spring? Right, go back to physics 101. Right, it's the spring constant K times the displacement squared, right? So Kx squared, right, is the potential energy stored in a spring. This is exactly the same thing. Our elastic modulus is the same as our spring constant, and then we have a volumetric strain squared, right? This 2/3 comes in because of the volume, right? So that if we were just talking about the strain energy, it's 1/2, right? Kx squared. It would be the same thing, 1/2 mu, the volumetric strain squared. We also have bulk modulus, shear modulus stuff. But in reality, that's not super important. It's just understanding that this is a strain energy per unit volume times the volume times a factor that corrects for the anisotropy in shape. And that gives us an estimate of the Gibbs free energy due to the coherency strains for a particle. Right? And as you can imagine, anytime we start talking about Gibbs free energies, you think this is going to tie into our nucleation theory, and it totally is. Right? So why does this matter is because the strain energy shifts our free energy curves. Right? And we'll talk about that in a little bit. Right? So before in liquids, we only had this is our bulk free energy, right? And we had a surface effect. And now we have to add in another effect, which is the coherency strain, which is going to reduce our driving force, right? So since we have to pay an energy penalty to create those coherency strains, we're going to reduce our bulk driving force, which is going to shift our critical radius out to higher values, right? And our Gibbs free energy activation hump to larger penalty, right? Which means that it's going to be harder to nucleate, right? If we have a bigger activation energy and a larger R star, we're going to have more difficulty nucleating. Okay, so let's hop into this with homogeneous nucleation in the last bit of time. Okay, so if we think about precipitation, right? I go from alpha, we're holding at this temperature, right? Let's just pretend we hold at this temperature for a long enough time that everything becomes nice and homogeneous. And then we rapidly quench it down. Now we're at this temperature, right? I have a very significant undercooling from the equilibrium transformation temperature from alpha to beta. Okay, so what has to happen in order to precipitate out this beta and get my system to where it wants to be? Okay. So first off, my B atoms within my alpha matrix need to diffuse together to form a small volume, a small region of the beta composition, which is way out here. So I need to diffuse B to form clusters of B atoms, right? That has the correct composition. Okay. Then the atoms need to rearrange themselves into the right crystal structure for beta, because alpha and beta can have different crystal lattices, crystal structures, right? And then we have to create the alpha beta interface during the process, right? Also, the volume of beta and alpha may be different, right? So now we have the coherency strains, and this is going to lead to our activation barrier, right? So the creation of the interface and the creation of the strain and the creation of the misfit strain, right, are the main drivers in the creation in our activation barrier, right? But we also have a little bit of an activation hump that's due to the local rearrangement of the atoms into the beta crystal structure, right? Because there's steric hindrance effects and things like that. You know, atoms need to move past each other, right? So that adds a bit. And then this diffusion here, right, is going to determine our time scale at how fast these things can happen. All of these steps require that we're able to move our B atoms together to form these clusters, right? So what does our activation barrier look like? Well, we have three contributions, right? We have our bulk Gibbs free energy, right? Right. Our system does not want to be alpha. It wants to be alpha and beta, right? So we can reduce our overall free energy with the creation of beta, right? And that's our volume free energy term, right? That's reducing the energy of the system. The creation of our surface area is going to increase the free energy, right? Back to our friend Gibbs-Thompson. And the transformed volume doesn't fit perfectly, right? So that's going to increase our energy as well, right? It's usually not phrased as a increase in energy per se, but a decrease in the volume free energy term, sort of for historical reasons, because this is volumetric and this is volumetric, so they get combined together, right? But so if we have here, we have our volumetric free energy is negative, our surface energy and our strain terms are positive, right? So we can calculate our volumes. Oh, dang it. This should have an r cubed here. 4/3 pi r cubed. Shoot, how did I lose it? I lost it on that one too. Dang it. Okay, everyone, right now, write in r cubed. Okay, so we have our volume terms where our strain subtracts from our bulk plus our surface energy. So what does that look like? Well, here's our volume term, here's our strain term, our surface energy term, and this is exactly the same as for nucleation of a solid from a liquid, but now we have a reduction in our driving force due to the strain, right? So this curve is really what we want, is our GV minus delta GV minus delta GS, our volume term minus our strain term. And that pushes this line out here. So that means we're not getting as negative as quickly, right? So that means our surface energy term dominates for longer, right? And when that happens, our activation energy hump increases, and our star gets pulled to longer and longer lengths. Okay, you can see our expression for R star and delta G star are exactly the same as for nucleation of a solid from a liquid, with the exception that instead of delta GV appearing by itself in the denominator, now we have delta GV minus delta GS. Other than that, the theory is exactly the same as solidification, right? Which is why we do that first, right? This is just an added little wrinkle, right? So you know everything there is to know now, right? Well, almost. But you get a sense of the physical picture for nucleation, okay? So if we think about what goes into the nucleation rate, right? Our concentration of critical size nuclei looks exactly the same as it did before, right? Right. What I want to know is how many nuclei of radius size R star. Well, I need to just plug in my Gibbs free energy here. Delta G star. This is the number of potential clusters that I have, right? And we have our Boltzmann statistics. And then in an analogy to solidification, if we take the number of attempts times the number of clusters, we get our nucleation rate. Okay. F here is a little bit more complicated because it depends on the surface area of the nucleus and the rate at which the atoms can diffuse to the cluster, right, to make it larger than R star. So it's not a simple, straightforward number like it was in solidification, okay? What we know is that this is going to be dependent on diffusion. How fast can our atoms diffuse? So we're going to have a delta Gibbs free energy of migration here, right? So our attempt frequency also follows Boltzmann statistics, right? And so we have a nucleation rate term that combines everything together, right? The nucleation rate has our delta G star term, like we saw from solidification, but now we also have a diffusion term. How fast can the atoms migrate, right? And it's the combination of these two exponentials that determine our nucleation rate, okay? And to add just another little wrinkle, these can be opposite in sign. Our Gibbs free energy for migration can be different than our Gibbs free energy for nucleation, okay? So what do we get? Right? You can ignore this figure here, figure B. This is super confusing and it's not really talked about in your reading either. So just ignore that. But the key important idea is here, right? In figure C. Okay? As we go lower and lower in temperature, we know that our driving force for nucleation increases, right? Same as solidification. The greater our undercooling, the more likely we were to be able to overcome our energy barrier, right? Okay. But what happens to diffusion with temperature, right? Our ability to move atoms is much higher at higher temperatures and low at low temperatures, right? So our driving force for the phase transformation increases with a bigger undercooling, but our ability to move the atoms decreases with a big undercooling, okay? So if we're up at near the equilibrium phase transformation temperature, we have a huge amount of driving force for mobility, right? We have we can easily move atoms around, but we don't have enough driving force to overcome our activation hump. So we have a very low nucleation rate, right? But there's going to likely be some temperature where these cross, right? And at which case we get a peak, a maximal nucleation rate. Our nucleation rate increases and then decreases, right? This is different than our nucleation rate for solidification, which just kept going out, right? It was like a step function. We hit our critical undercooling and boom, we got a huge spike in nucleation rate. Here, we have to take into account our mobility. So we get an increase in the nucleation rate at some critical undercooling that reaches then a maximum and then decreases down to zero, right? And this is important because this is how we quench in a desired microstructure, right? So what we may do is, obviously, if I go from alpha down to room temperature, I no longer have mobility, right? So I'm going to stay at pure alpha. But if I come down and I hold at some intermediate temperature, I can get precipitates to form, right? Because I have a finite nucleation rate. Once I get the precipitate structure I want, I can then quench down to room temperature. And because I don't have any more driving force for diffusion, I'm able to lock that precipitate structure into place. Okay? So this is where we really see the difference between thermodynamics and kinetics. Thermodynamics says, if I hold here, I'm going to go to alpha and beta. And yes, that's true. If I hold it for geological timescales or universal astronomical timescales, that is true. But over the course of the lifespan of the part that my material is made out of, I'm going to stay at where I am. I'm going to stay at pure alpha if I just quench down to room temperature, because I don't have a sufficient atomic mobility to form my secondary phase. Okay, and so that's where we're going to stop, right? This is really the only new concept in that we want to talk about in terms of diffusional solid state phase transformations, right? Well, actually two, right? We have the strain energy component and the fact that the rate also depends on our ability to diffuse, right? And you can also guess that phase transformations such as massive that don't require long-range diffusion have much higher nucleation rates than those like precipitation and eutectic transformations that do require long-range diffusion. Okay, so we'll stop there. We'll see everyone Wednesday. No, I shaved in a horrible, weak moment of judgment. So yeah, it was a bad mistake. It'll grow back. Luckily it grows back fast. So I wouldn't call this looking sharp. The analogy that I said in the early chat is, yeah, I will definitely not be shaving this November. I think I look like a low-level mobster who just got sentenced to 20 years in prison and broke down crying in the courtroom. The lack of facial hair really highlights the bags under my eyes and the puffiness. So yeah. Okay, well, have a good weekend, everybody. Let's hope that society is still in one piece for Wednesday. What story? Okay, well, so yeah, it's going to be a crazy Tuesday no matter the outcome. I just hope that
this isn't going to end for another couple of weeks, probably.
Well, I know that, but what I'm really hoping is that there is no violence at polling places tomorrow. Is really my big concern, because if people with guns show up and violence starts, especially if it appears to be racially motivated, every major city in this country is going to go up in flames. Yeah, we're in a very different situation than we were in 2020. So I hope, I sincerely hope that everything goes well and we can have a little bit of normalcy from lecture on Wednesday in maybe a tense and divided but still hanging together society. Okay, if you haven't voted and you're eligible to, please do, because right, that's how we all make our voice heard, right? And young people are historically underrepresented, right? So I think this election tells all, right? You've got a choice between two old white guys who are going to be deciding how your futures look, right? So I'm really optimistic by how much people, young voters are getting out. What I think is really interesting is young voters on both sides of the political spectrum are being energized. So as far as I'm concerned, that's a good thing, right? Even if I don't agree with the politics, I want to be very careful, because I want to steer as clear as possible away from anything that might smack of trying to push things for one side or the other. But young people being engaged and young people making decisions about their own future is really what needs to happen. And as long as you guys allow old people to be in charge, things are not going to get better for you, right? And we'll leave it there. Okay. Have a good one, everybody.